Okay. Okay, so while we're still setting up and getting that mic to work, it's now my pleasure to introduce the first early career research spotlight directly after the keynote. And it just so happens that maybe it's related to the topic we were just talking about. But the awardee in this case is Khimya Khetarpal, my bad. And she's done a lot of really nice work. Right now, she's at Google DeepMind and is affiliated with Mila. She's also previously done her PhD at McGill and Mila with Doina Precup. She's done a lot of contributions to Continual RL, which is why she's very deserving of this talk here. And you'll listen to some of this hopefully in the talk, but also you'll listen to a nice vision on how to unify agent perception, behavior, and cognition by looking at how to navigate the affordance landscape in reinforcement learning. So I'm very excited to hear about that, and I'll just leave the stage to you.
Hi, everyone. My name is Khimya Khetarpal, and very happy to be here. And today I will talk about navigating the affordance landscape for continual agent adaptation. So most real-world problems, such as this robot navigating in a household, are open-ended. And they require AI agents to efficiently represent the world's knowledge with the ability to continually adapt to changes and become better learners over time. State-of-the-art methods demonstrate super impressive capabilities. However, much of these gains are a result of leveraging significant amount of demonstration data. So for instance, looking closer at the data used to train these state-of-the-art methods, they collect a large-scale teleoperated robot action data set over a period of 12 months, which consists of thousands of hours of real-world expert demonstration data. Yes, it is very diverse, it has a lot of tasks, and it covers a broad range of capabilities that we would like to see in our agents, but this is all human demonstration data. In this talk, I argue that for AI agents that the ability to efficiently adapt to new scenarios with limited data is extremely crucial for us to be able to deploy these agents robustly in open-ended situations, such as a home, or examples that Martha spoke about earlier, a city. And that's why it's really important for us to inculcate this ability in our agents to be able to efficiently adapt with limited data and not a ton of data. To develop such an ability, I equip RL agents with three fundamental components of learning abstractions: learning the world model, which is a representation of the knowledge that the world has, and the ability to plan and search, all towards the goal of building agents or systems that can continually learn in a real-world situation. So how should an RL agent efficiently adapt to new scenarios with limited data? Humans undeniably possess a very general sense of intelligence. Both animals and people understand the relationships between the features of the environment and the actions that are feasible in those features. For instance, both babies and animals here know that it is affordable to crawl on a rigid surface, despite the surface being wood or carpet. Gibson coined the term affordances to describe such relations in the context of embodied agents acting in a physical world. Understanding which situations afford which behaviors has multiple potential benefits in our goal to instilling general intelligence in agents. For instance, it will allow for agents to better generalize. If a robot or an agent understands that a doorknob affords opening the door and going through it, then no matter what the door, it should be able to use this information in many different situations, enabling it to adapt faster and be efficient in planning. We formalize this notion of affordances in reinforcement learning by considering the desired outcome of an abstract action or an option, which is the intent associated with that action. also referred to as the temporally extended intent. Affordances then constitute the subset of the state and abstract actions which will achieve those goals or end results based on these intent specifications. We have leveraged this foundation to first formalize affordances in RL by considering the desired outcome of a primitive action. That is the intent associated with that action. Then we generalize this notion to temporally abstract actions, allowing us to build partial models of the world that are compact and much more efficient to plan with, as opposed to building a full model of the world, which will end up modeling everything which may or may not be useful. In a follow-up work, we analyze the agent's decision-making process with competing affordances at any given point, characterizing how affordances are able to capture the spectrum of attention, going from soft attention to hard attention. In more recent years, we proposed an interpretable analysis of multi-scale, multiplayer game human behavior in Xbox games by using this lens of affordance, more amenable to the cognitive science literature of task sets. This led to an interpretable framework allowing us to compare human and AI behavior and their alignment in the latent space. We are now interested in navigating the affordance landscape in much more open-ended domains. So first, let's talk briefly about web agents. For web agents, the observation space is this web page UI, and the task is a text description on top of the image. The action space is super large, which I'm here denoting by these red grid cells, indicating all possible actions that the agent can click on this web page. To solve this problem, we propose a method called code as generative affordances. Also can be just short acronymized as COJA. So COJA here is a method that leverages pre-trained VLMs on top to generate code or programs that determine affordable actions using a fully automated program generation and verification pipeline by using some unit test cases. The generated code is then used in the loop of an RL agent to return a set of affordances given a pixel observation to greatly reduce the number of actions that an agent must consider. So, is that a train?
I think it can be something like wheels
Okay.
on the top floor. Not a ghost.
Right. So maybe it gives us a minute to look at the diagram more in depth. So these programs are generated offline prior to training with this box on top. And the idea is that they are meant to be reusable and generalizable across many different tasks. And once they have been generated using a fully automated and like generation and verification pipeline, they are then used in the loop of an RL agent, which is being trained using online reinforcement learning. And what ends up happening is this program spits actions that are affordable, leading to an affordance masking technique that masks out all the huge space of actions that are not useful in a particular given task. We demonstrate on a wide range of tasks in Mini WOP++ benchmark that COJA is orders of magnitude more sample efficient than its RL counterpart. As you can see here, the orange lines are COJA, the bars are COJA, and the blue ones is its vanilla RL agent. Moreover, what's most important is that COJA's affordance scripts are reusable and generalizable across a family of tasks. Of most importance, though, is to note that if you have a large enough number of demonstrations, imitation learning might just be the right mechanism to use for a particular task or a bunch of tasks as well. However, if you start stripping behavior cloning down with the number of expert trajectories it's provided from 1,000 to 200 to 50 to even as minimum as 10, behavior cloning struggles and starts to degrade heavily in performance, as indicated here as you go from left to right in this, or right to left in this plot. However, with this limited amount of demonstrations, as you notice that Koja performs better compared to behavior cloning agent when there is such little expert trajectories available. Next, if you consider another open-ended setting, such as an off-road navigation for robots, which is an autonomous task, it can be thought of as a simple agent, big world setup, which was proposed by Ben Roy and colleagues, where the agent is super small, but the world is super big, which is perfect for a continual learning example of a real-world setting. And the agent is not really aware or doesn't really have a full, complete map of the environment. So it needs to figure out as it goes on this robot navigation task what to do. Here we make a key observation that in this open-ended setting, effective long-range navigation only necessitates in identifying good frontiers or good immediate directions for planning instead of needing to know the whole map and the entire world knowledge. With this observation, we propose long-range navigator. So LRN learns affordable frontiers at intermediate representations, resulting in a more efficient and safe capability towards these goals. So what happens is that there are two levels to it. So you can think of it as a hierarchical method where the long-range navigator first learns to identify what are the affordable frontiers, and then it ends up picking the one that aligns best with the goal vector or the goal heading to where it's supposed to go in a big open-ended environment, like an off-road robot navigation task. One key takeaway here is that better affordances translate to more efficient paths. It enables robots to make less myopic decisions, facilitating the long-range navigation with only incomplete knowledge of the environment. More importantly, this entire pipeline is trained entirely on unlabeled, egocentric videos, making it scalable and adaptable. However, note that in both these real-world problems, there is non-stationarity, and it is vital to continually learn and adapt. If you recall, in Koja, these programs that are once generated are not really adapting or self-improving on the fly. So that's a capability that's still missing. And same is the case for LRN. While we have really good performance across a lot of unseen environments, and we are able to generalize pretty good just by the power of knowing what affordances are in which situations, these affordance maps or heat maps are not really adapting on the fly as the agent continues to live and breathe in this open-ended situation, which is what I would like for us to think about and go towards. So let me motivate this further. Why? Because theories of embodied cognition and behavior suggest that adaptive selection among currently available affordances is not just biased by the predictions of their immediate outcomes and payoffs, but it's also biased by the future outcomes and the payoffs that they might enable. So what we are saying here is that, or rather what Paul and Sisek and Giovanni are saying here, is that this will allow animals to purposively create new affordances that they can later exploit to achieve high goals, and ends up resulting in an intentional action as opposed to trying to imitate what's there in the training data. So to me, this offers a really powerful concept because it doesn't just limit us to the current situation or what's affordable right now or what was in our training distribution in, let's say, behavior cloning or imitation learning, but it has the power to unlock new affordances which the agent might create as it's learning in the environment. So going back to this example or the application that I would like to see deployed is this open-ended situation of robot in a household. I argue that this requires us to rethink the agent-environment interaction, perhaps through the lens of affordances, and position that navigating this affordance landscape can indeed enable continual adaptation. So to study this, we consider the sequential task setting. To just trying to formalize this, I go from this open-ended to this situation where a robot is continuously in a sequential manner presented with any possible task. And the objective is that the agent has to perform a sequence of these tasks. The agent learns from the environment by trial and error. So the agent has no a priori knowledge of the task that is going to be presented with, or the number of tasks that are incoming. Or neither the precise description of the task, like get me a coffee or anything. It's really an online reinforcement learning problem, but posed in a sequential decision-making setup. So notice that the key to understanding affordances is that they depend both on the agent and its environment. And it's not just a function of one or the other. So let us consider three axes: the physical workspace, the robot embodiment, and the distribution of tasks. So the agent here is defined by the robot embodiment, for example, a robot arm gripper or a mobile robot. The environment is defined by the bounds of the robot's physical workspace, example, a tabletop robot, or in the case of an off-road robot navigation, really the entire space of physical space surrounding its situation. The third axis is the distribution of tasks. So sequential decision-making tasks are sampled from a certain distribution, but this can be a changing distribution and not necessarily a stationary distribution of one typical kind. So I'm just showing three different types of tasks, where one might be one type of a gripper, another might be another type of a gripper, it could be a bimanual robot, and the third might be a separate embodiment than you have already seen. So our goal here is to use this lens of affordances to revisit this agent-environment interaction in this open-ended setting. And to do so, we purposely draw the boundary between the agent and the environment by categorizing intents into two classes. One is the task-agnostic intents, or the distribution robust, which are based on an agent's internal dynamics. So for example, if I consider a robot arm gripper, then depending on the internal dynamics of the gripper, a bunch of intents are agnostic to a big distribution of tasks. So pick and place is agnostic to no matter if you give me letters or if you give me blocks, and that's very contextual and dependent on a particular embodiment or the internal world model of an agent dynamics. The second class is task-specific intents, which captures the set of intents that the environment or the physical workspace poses. Now this, if you notice, is dependent on both the physical workspace and interleaved with the task distribution from which we are sampling. Now, given a distribution of task-agnostic tasks and a set of task-agnostic intents, a set of affordances is intrinsic to an agent, or therefore termed as distribution robust agent affordances, if the probability of that affordance does not satisfy any intent in that task distribution, only bounded by a certain value. So it has to meet a lot of intents in this task-agnostic intents to be a distribution robust, to be robust to that distribution of tasks for that particular agent embodiment. So in other words, task-agnostic intents result in distribution robust agent affordances that are intrinsic to an agent and are robust across a bunch of tasks or a big distribution of tasks. Such as, like I said, a block can be picked only when nothing is on top of the block, or a block is movable when it's actually present in the scene or the environment that I'm considering. At the same time, there are affordances, a range of affordances that emerge at the boundary of the interaction, of the agent-environment interaction. That is, they are local and they are contextual, depending on both the robot embodiment and, as I said, the physical workspace interleaved with the task distribution that the agent is presented with. For example, only a specific combination of blocks match for this Lego task to be completed successfully. Similarly, placing a block inside another one, or maybe only be possible in a small number of situations when the right sizes of hollow objects are available to actually make that specific arrangement possible. So task-specific intents result in task-specific affordances to emerge at this interaction. So leveraging this lens, how can we instantiate affordance-mediated agency for improving efficiency in the era of large models or foundation models? So we posit that a large model can be thought of as a world model or a transition dynamics model, given that it has consumed the internet scale knowledge. However, this knowledge is trying to model all possible things in the internet, every possible text, every possible rule, making it analogous to a full world model. Think of it as like modeling the world at a pixel by pixel level, and half of it is it's impossible for humans to model at that scale. So similarly, we say that it's intractable and inefficient for our agents to plan with such a huge intractable world model. Now, to remedy this issue, we propose to use large models as partial models in action value estimates, thus substantially reducing their search space. And when I would do MCTS or planning, this would substantially reduce the branching factor, improving the corresponding action value estimates with high confidence, as opposed to having lots of estimates, all possible things with distributed confidence and having lower certainty of the action value estimates. Now, we achieve this in particular by leveraging this notion of affordances that I've been talking about, where we provide large models with the task agnostic intents as a prior to begin with in the prompts. This leads us to giving us a subset of state and actions that are affordable, and therefore induces a partial world model which only makes predictions on state and actions that are in the affordance set. So it ends up playing the role or inducing a partial world model, even though structurally the model is already pre-trained, so it is capable of making all possible predictions and making all possible paths as search paths. So here is a small result where we show that inducing a partial model via affordances is more efficient in search. But of course, because of no free lunch, this comes at the cost of the induced bias from the affordance accuracy. So if you look at the first row, this is basically a full model with few short examples, which never gets to the right score. It exhausts its budget provided for the search and requires a large number of calls. Despite that, it never really completes the task in the given budget for the actual episode. However, doing the same thing, but by inducing a partial world model, actually leads to more efficiency in search, but of course at the cost of the induced bias from the accuracy of affordances, because in the third row, you see that if you had the perfect affordances, then you would not suffer from that bias. So this, of course, comes at a cost of how accurate are your intents and how accurate is your affordance set, and have you missed something important that was supposed to be in the affordance set. So next, I consider access to a perfect world model. So I'm motivating here the need to adapt these affordances, because even with a perfect world model, x-axis is showing the different levels of accuracy that is achieved in the affordance. So if I have perfect accuracy on the bottom left, I can get up to 100% performance with a perfect world model. But even slight changes to the affordance accuracy plays a very important role. This is for one fixed task. Any errors in prediction of the affordances translates to catastrophic failures in the performance of the MCTS policy, especially given a certain budget of search and given a certain budget of steps in the episode for that particular task. Now imagine that your task has changed and you are in a continually open-ended environments that we have been talking about. So imagine in that situation, a lot of affordances are going to emerge at this boundary of the interaction and requiring for the agent's belief over affordances to be adapted over time. Because what was affordable in this particular situation may not be affordable in the next task, and so on, because the world is ever changing and I, as an agent, need to adapt my belief the way to adapt our belief is by grounding the agent's belief by real world interactions in every task. So in essence, when operating in an open-ended world with a sequence of incoming tasks without any prior knowledge, interacting with the real environment allows the grounding of this belief over affordances, by some mechanism of an agent adaptation module. So notice that this agent adaptation module should then feed back into what your prior belief was over what's affordable, which is based on what we fed into intents. So I could very well have a misspecified intent in the beginning. I could have an intent based on my understanding of whatever I have been trained on a huge amount of demonstration data. But well, I'll never be able to cover the long tail of the distribution, and my intents might be completely misspecified in the new tasks that I'm facing, and so on. So therefore, we really need the agent to interact in the real world, gather real experience, and use that experience in an adaptation module and update its belief over affordances over time. This leads me to the final thoughts on like, how do you really do this agent adaptation with limited data? Well, there are many ways we can go about this. One common way and the simplest thing to do is to do in-context adaptation by actually providing this real-world experience and few-shot data in every new task back into your context and update your belief over affordances. So something like this can already yield decent gains in simple settings with a few examples. But there is also a downside that this can be really fragile and is less principled because, well, you can write the prompt in many different ways and you can do all possible ways of scaffolding your prompt and come up with different solutions. Another commonly used approach is fine-tuning on a specific downstream task. So this leverages offline data. It doesn't really depend on online training during test time. And however, the one thing that I'm not very sure how well can it be really open-ended is because it ends up being narrow in capability to the task that you are fine-tuning on. But maybe it's perfect for if your end goal is mastery in certain range of tasks only. Let's say you want to master how to navigate in this particular auditorium and you don't really care about as open-ended world as I do, for example. The last one, which is most that I'm interested in exploring further, is online adaptation, or actually on-the-fly adaptation, where the biggest pro here is that it really captures the actual problem that the real world is non-stationary in real time. So we should be able to use the few-shot data or experience from the interaction with the world and adapt just as humans do over time. This offers the potential to be seamlessly integrated in open-ended learning environments as well. Finally, in closing, the ability to efficiently adapt to new scenarios with limited data is crucial to enable rapidly deploying robust agents in such open-ended situations, for example, a household. And I'm arguing that navigating the affordance landscape can enable continual adaptation simply because of the nature of how affordances emerge at the agent environment interaction boundary. Finally, adaptation in the presence of limited data, I believe, is vital for us achieving AGI, because even for the tasks that we can gather unlimited data, the ability to quickly adapt will still lead to more intelligent agents. Moreover, data collection is expensive, and we cannot really rely on expert demonstrations forever. And it's intractable to collect all possible scenarios. So there is that inevitable imitation gap. And I want to thank all my collaborators and 2 students who I work with who led the work on CoJA and LRN. Yeah, thank you. Happy to take any questions.
Thank you. We have maybe time for 2 or 3 questions, running slightly into the coffee break, but it doesn't matter. Does anyone have a question already? If not, then I'll start with one while you think about it. So I was wondering, for the affordances, like a lot of the objects in our real world are kind of like constructs of society. So like a cup is only a cup if I say that water should be pulled in there. There could also be like, it could be a pencil holder, right? Like in my chair, it can be a chair, or it could be like a rack for clothing and so on. So is there like room in your triangle for the fact that like affordances are super highly contextual in the first place?
Right. So I would say that that can be thought of as contextual or local affordances. So you're saying that if for me, a chair affords sitting, but for someone else, a chair affords a pile of clothes that are waiting to be folded. So, you know, you could think of it as like, depending on the agent environment interaction, in the beginning, you had a belief that your intent was to sit, and that affordance came up in the first task, your affordance was met accordingly. But over time, you could use this framework completely to adapt your belief depending on the context. So definitely that completely fits in this situation.
Okay, thank you. Now, anyone else have any question in the meantime?
Yeah, happy to chat over coffee as well. I know.
Yeah, I guess also what we can do is, because we're running behind schedule anyway, we can go into the coffee break. Thanks, Khimya, again for the very nice talk.